G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. This is lecture 4, so just getting in preparation, getting ready for assessment 1. So I'm only going to cover 3 things. I had a list of 5 things, but I've cut it down, put these into lecture 5 for the second test. So I'm just going to go through limit theorems, monotone sequences, and convergence sequences. So that's all we're going to be doing in this lecture. Okay, so this is a visual of limit theorems, and you can see here, if you look at the red line's getting closer and closer on the bottom to -1, and closer and closer on the top line to 1. And so that would be, my image down a little bit more. You can see limit inf on the bottom there, and lim sup. So they're the superior limit and the inferior limit. And that's 10 where xn just keeps on going and going and going, and that's really, these are becoming the limits of this series. So the sequence xn, which is the blue line, or the blue wavy line, is approaching the 2 curves from above and below. And so they're called limit superior and limit inferior, and the abbreviation is lim sup or lim inf, which is the same sort of thing. So in this case, the sequence goes on indefinitely between 2 limits and just goes on and on and on. And so that's what a limit theorem is, or is describing in terms of limits, some sort of series which gets closer and closer to certain limits. So if we just look at the main theorems in set theory, this before the theorem, a sequence of sets is an ordered collection of sets denoted as bracket A with lowercase n bracket, where n is a natural number. In other words, 0, 1, 2, 3, 4, etc., etc. And here we go. Here's our theorems. So the first one, limit superior, or lim sup of an, I should actually have that of a lowercase an, but it doesn't matter. The lim sup is the largest accumulation point of a sequence. If there are infinite points, the limit superior can tend to n goes into infinity of limit sup an. Similarly, limit inferior, the lim inf of a sequence, is the smallest accumulation point of a sequence. If there are infinite points, the inferior limit can tend to lim inf of negative infinity, so n going to negative infinity of an. Convergence of sets. A sequence of sets an is said to converge if its lim sup and lim inf are equal. And this applies in reverse, and this is a standard thing to accept. Lim sup and lim inf are equal if and only if, there's that double F, the series is convergent. So the only chance of those two being equal is if the series is convergent. And if the series is convergent, it applies in reverse. Then lim sup and lim inf will be equal. Okay, and I've got a link there, maybe it's just in the way, a link there which you can go to. It is in LibreText, so you could type in LibreText limit theorems and it will come up. LibreText is pretty handy to read through to get this level of mathematics. Highly recommend it. Monotone sequences, and again, type in monotone sequences. Same thing for LibreText. I've got the link down the bottom, which you can look in the notes. So a sequence an is increasing if an is less than or equal to an plus 1 for all n is part of the natural numbers. A sequence an is decreasing if an is greater than a to the n plus 1 for all n as elements of n. And this will be the equivalent of in high school, where you've got a geometric series where the ratio is greater than 1 or less than 1, and you've got an increasing or decreasing type of series. If a sequence is increasing or decreasing, it's regarded as a monotone sequence. So if it's always increasing, it's monotone. If it's always decreasing, it's monotone. And it doesn't have to decrease by the same amount. It could be decreasing by a percentage amount, a fractional amount, etc., etc. If a sequence an is monotone, either increasing or decreasing, then a limit exists and is equal to the union for increasing sequences or intersection for decreasing sequences of the sets in the sequences in the series, in the sequence. And I've done the symbols on the next slide. So just saying that again, if the sequence is monotone, either increasing or decreasing, then the limit exists and is equal to the union if it's increasing, or intersection if it's decreasing, of the sets in the sequence. Okay, try and get that one, memorize that one, it's helpful. And there's the Libra text link, which you can look at in the notes. Existence of limits. If limit an exists, then for any set B, the limit of an union B equals the limit of an union with B for monotone increasing, and the limit of an intersection B equals the limit of an with the intersection of B for monotone decreasing. So that tells you that there is, that tells you that there exists a limit. Okay, union increasing, intersection decreasing. Examples, because we love examples, because that really helps understanding, and they're also going to be the things that you're going to question on in a test. Okay, so let's consider the sequence of intervals. An equals bracket 0, comma, 1 minus 1 over n, bracket. Is this increasing or decreasing? And so this is a sequence of intervals, so lengths from 0 to this point here. So these are intervals. Is this an increasing or decreasing? So really easy to test it out. Start putting in some numbers. So if you put in 1, you get 1 minus 1 is 0. So that's 0. If you put in 2, you get 1, and 1 minus 2, sorry, 1 minus a half is a half, so 0 a half. You put in 3, 1 minus a third is 2/3. Put in 4, 1 minus a quarter is 3/4. And you can see it's getting a half, 2/3, 3/4. It's getting bigger and bigger. So it's an increasing sequence. And you might be good enough to just look at that and go, yep, that's going to be an increasing sequence. And that's great. Yeah, God bless you. I like doing some little examples. That helps my brain in thinking what's going on. What is the limit? And in other words, what is it as n approaches infinity? So the limit as n approaches infinity is 1. So if this keeps on getting bigger and bigger, well, this keeps on getting smaller and smaller. So 1 minus not much or nothing ends up being 1. That's pretty easy. Consider the sequence of intervals an. So this is a second question. An is 1 on n to 2. Is this increasing or decreasing? And again, you might be able to look at that and just know, oh, I know what that is, which is great. God bless you again. But again, I'm going to do examples. So I'm going to put in 1. 1 over 1 is 1. So we get a 1 and 2. So that's the interval. And then we've got from 1 over a half. That's the sequence is decreasing, but the length of the intervals is actually increasing, isn't it? So from 1 to 2 is not as long as a half to 2, which is not as long as a third to 2. So the length of the interval is increasing. This will be a tricky question to answer. So here, it's a decreasing sequence. Yeah, that's pretty obvious. 1, a half, a third, a quarter. But if you're asked this question, it'll be really helpful if you answered it. It's a decreasing sequence, but the length of the intervals is increasing. Didn't think of that before. Just looking at that now, that's length 1, that's length 1 and a half, that's length 1 and 2/3, that's length 1 and 3/4. So the length of the intervals is actually increasing. The sequence is decreasing. So that will be an interesting question to answer. And I think you should, like if I'm answering this in an exam, I'm going to answer the sequence of 1 over n is decreasing. The length of the intervals is increasing, so that you don't, so that the examiner knows, hey, this person's actually paying attention, because it's a sequence of intervals. So, yeah, bit interesting there. This one, on the other hand, you can see the numbers increasing, and because it's starting from 0, the length of the interval is also increasing. So that's an increasing sequence. Whereas this one, the sequence is decreasing, but the length of the interval actually increases. So decreasing sequence, what is the limit? Well, the limit is obviously zero, because as that goes to 1 over infinity, this becomes zero. So you get the length of 0 to 2. So yeah, very interesting question to answer there. Pay attention to that. You never know, it might come up in a test. Okay, third one. This question here is the last question in terms of an example for this lecture. What I want you to do is write this out because there's 3 steps to this, and then do it again. So write this example out twice, because this will be assessed, and almost certainly it'll be assessed, certainly in the first test, but almost certainly will be assessed in the final test. So I would pause the video occasionally to write this out, and then turn the video off and do it again for yourself, practice. So write this out twice. That's my encouragement to you. Okay, so prove the following sequence has a limit and determine what that limit is. So A1 is 2 and AN plus 1 is A base n plus 5 over 3 for all n greater than or equal to 1. So this is the formula for the limit, and here's A1 and AN plus 1. So prove the following sequence has a limit and determine what that limit is. So here we're placing them at A1 and AN plus 1 and paying attention that this is AN plus 1. So it's adding on whatever was this one before it. First, we're going to prove by induction, and it's really good, I think, here that we've got 2 steps. Both of them are induction, which you will have done in high school, so you should be quite used to it. It might not be fresh in your brain, so this is a good practice for you. First, prove by induction that AN is less than or equal to AN plus 1 is increasing for all n as elements of the natural numbers. So that's our first step. So we're going to write, given A1 is 2 and A2 is A1 plus 5 over 3, that equals, well, what is A1? A1 is 2, isn't it? So we're going to put 2 in there. 2 plus 5 is 7 over 3. And 7 plus 3 is greater than 2. Therefore, it's true for n equals 1. So that's the first step of induction. Prove it's true for the first term. In this case, n equals 1. Now we're going to assume it's true for n equals k. So k plus 1. So we're looking at this formula here. We're looking at this formula. K plus 1 equals a to the k plus 5. And we're going to say that is less than or equal to k plus 2. And we're really reflecting this thing, so that the lower term is less than or equal to the bigger term. So k plus 1 is less than or equal to k plus 2. K plus 1 is ak plus 5 over 3. Ak plus 2 is ak plus 1 plus 5 over 3. We're assuming this is true. Put a red star there so we can refer back to it. You can I'd put some sort of big star, cross, whatever, happy symbol, whatever symbol makes you happy, put a symbol on that so you can refer to it later, because as with all induction proofs, you refer to it later because that's how it goes. So we're assuming it's true for that. Now we're going to show it's true for n equals k plus 1. So now we're going to show k plus 2 equals this, which is ak plus 1 plus 5 over 3, is less than or equal to ak plus 3, which is ak plus 2 plus 5 over 3. So we want to show this is true. So now what we're going to do is we're just going to grab the formula part of it. We're going to ignore ak plus 2 and ak plus 1. We're going to grab the formula part of it, and so we want to show that. So we're going to keep those going. We're showing that this is true. So we're just going to simplify. What I'm going to do is take out the 5 over 3. So this is just ak plus 1 plus over 3 plus 5 over 3, which is there. This is ak plus 2 over 3 plus 5 over 3, and I've just separated that. Pretty easy, pretty basic maths. So now I can cancel the 5 over 3 because they're just constants. They don't make any difference. So now we've got ak plus 1 over 3 is less than or equal to ak plus 2 over 3. So now I've got divided by 3 on both sides. I'm going to multiply both sides by 3. I probably could have put in brackets here, multiplied both sides by 3, but I'm telling you what I'm doing. So now I've got ak plus 1 is less than or equal to ak plus 2. Now, Dum da da. Where have we seen that before? Oh, look, the red star. So this is true since this is our initial assumption. So therefore we've done it. We've proved by induction that AN is less than or equal to AN plus 1. Okay, we've proved that that's increasing because we've proved that the lower term is less than the bigger term, and we've proved it by induction. So we're done. So that's our first step. Second step, show it is bounded. So now you could be tempted to think this. This is very easy because I thought of this and I thought, if I think of this, possibly you'll think of this. So you could go, as n approaches infinity, I could just go a n plus 1 is infinity because that'll just be infinity plus 5 over 3. Therefore it's infinity, therefore it's unbounded. And you'd be wrong. Okay, so don't think that. It's really easy because I just jumped in. I thought, oh, boom, boom, boom. I thought, oh, hang on, don't do that. So this is a sequence where these are getting replaced. AN plus 1, this AN is going back in there. So remember we put 2 plus 5 in there and got 7 over 3. Don't be tempted to just throw in infinity and go, oh, I'm jumping straight to infinity. Fantastic, I'll just put infinity in there. Bop-bom, wrong. What we need to do is do it by the series and see what's happening. So we're going to do that. Let's take it one term at a time. A1 is 2. We know that. So A2, 2 plus 5 over 3 is 7 over 3. And I've written it as a decimal, so it's approximately equal to 2.3. I'm going to use the approximation. Just for simplicity, I'm not going to use the fraction and get it to be super perfect, but you'll get the idea of what's happening. So now A3 is going to be 2.3 plus 5 over 3, which equals 7.3 approximately over 3, which again is approximately equal to 2.43. So now we're seeing a pattern. 2, 2.3, 2.43. Let's do it again. So A4 is going to be 2.43 plus 5 over 3 equals 7.43 over 3. Again, put in my calculator, you get 2.47. So now you've got a pattern 2, 2.3, 2.43, 2.47. You can see it's slowing down. It jumped by 0.3. Now it only jumped by 1.3. Now it only jumped by 0.04. And if you kept going, you could see this would slow down. Okay? So should, that should be, we can see it is bounded. That's obvious. As it's obvious, it will be less than 3. That should be a C there. Apologies for that. So again, we'll use induction. A1 equals 2, which is less than 3. So that's pretty obvious. What we're seeing is this number here is just not going to reach 3. There's no chance it's going to reach 3. So we see A1 equals 2, which is less than 3. That's true. So now we're going to do AK. AK equals AK plus 5 over 3. And we're going to put 3 in there because it's not going to reach 3, which is 3 over 5. And 3 plus 5 over 3, because we're saying that's our limit. 3 plus 5 over 3 is 8 over 3, and that does not get to 3. So it follows that AK for everything will be true, will be less than 3 for all n. And so, oops. So therefore, we've shown it's bounded. We've shown it's bounded by 3. It's not going to get to 3. We could have picked another number. We could have picked 4 and said, look, there's no chance this is going to get to 4. But you try and pick the number that's closest to what it's not going to reach. You can say, yeah, well, I'm going to say it's bounded by 3 because it's just not going to get there. So, yep, I've showed it's bounded. I'm not saying that's the best bound. I'm saying I can look at that and go, yeah, there's no chance that'll get to 3. Equally, I could say, oh, there's no chance it'll get to 4. So I could have used 4. So don't be scared that you've picked the wrong number to show that it's the bound. You don't want to be using 10. I mean, that's a bit stupid. But using 3 is a good plan. You could potentially here use 2.5 if you went a bit further and maybe 2.6, 2.7 and get a more accurate number, but 3 is pretty good. Like I said, you could use 4, but using 10 would be a bit like the assessor would go, really? You're picking 10? You're not really having a real go at seeing what the bound is. You're not getting very close to what the bound is. Okay, third and last of all, so these are the 3 steps. Third, we find the limit. we know that AN, because we've just shown that AN is less than or equal to AN plus 1. So that means that AN plus 1 is less than or equal to AN plus 2. So once we've shown it's true for this, we know it's true for this. And the monotone convergence theorem says that there must be a limit if it converges. So we've shown that it converges by those two steps, those two previous steps we just did. That proves it converges. So therefore, there must be a limit. Now we know it's bounded by 3. Like I said, you could have picked 4. But we know it's bounded by 3, so the limit's got to be 3 or less. So we can say that that all the instances of AN will converge to some limit L. So in other words, if we look at this equation, we can say that every single instance of AN plus 1, AN plus 2, AN plus whatever, will converge to some limit L. Okay? There's no chance it won't because the monotone convergence theorem says there must be a limit, and we're saying it's L. So what we're going to do is we're going to put L in here and here. We're going to put it in both positions because that's the limit. Because as it gets closer to the limit, these two will be closer and closer and closer together, which we saw happening as it got closer and closer together. So that will be the limit. So L will equal L plus 5 over 3, because it'll just get so close to this limit that you're putting in virtually the same number to get the same number out again. So what we'll have here, multiply both sides by 3. Really simple algebra. 3L equals L plus 5. Subtract that L, and we get 2L equals 5. Divide by L, and we get L equals 5 on 2. And that's it. That's the limit. Okay, so your homework, whoops, so get back there. So that's the limit just there. And that's really all you're doing. You're finding the limit by knowing, okay, it converges to some limit, which means that as we get closer to that limit, these two will be super, super close to each other because it's converging. It's getting closer and closer and closer to the limit. So we can just put the L in both positions and then just do algebra to figure out what that L is. And L in this instance will be 5 on 2. And what is 5 on 2? It's 2.5, like I sort of mentioned previously, that you could have guessed that, but it's possibly too close to guess if you're thinking, well, it might not be 2.5. So I've picked 3. Like I said, you could have picked 2.7, you could have picked 4, but you've got to pick something reasonably close to it to say, yeah, I can see that it's converging and it definitely won't reach that number. So here we can see the limit that it converges to is 5 on 2, which is 2.5. That's all I've got for you this week. This is LibreText. I want you to go and look through that, read through those. It's a bunch of pages in LibreText. Very helpful for you. And I will make up a whole bunch of questions for week 5 in preparation for the test. I'll get that done early and post it by next weekend. That's it. God bless you. Stay safe. Hope your study goes well. And yeah, I'll see you next time. Okay, bye.